Okay, welcome back. Day after Halloween, and you made it. It's pretty good. Probably a big night. At least we had a big night. We had like all these kids over, like a gang going through the neighborhood. They're all hopped up on sugar, but it was pretty good. And all sorts of stuff. Some Greek gods. My older son was a taco Luigi, like a Luigi outfit with a taco on. And constantly people are like, is that a new Mario power up? Like, what is that? He's like, it should be. It's like, all right, yeah, that's true. It'd be like a cool Mario Wonder kind of power up, like Taco Mario. But anyway, it was good. So we're back. We're doing linear algebra. And this is meant to be like as practical as you can get for linear algebra. Like we're gonna look at some of the algorithms and like how they work. The reason we do that is so you understand like when things fail, why are they failing? So your main tools for that are thinking about like singular and ill-conditioned. So if you're checking the condition of your matrix, that tells you how well you can solve a problem. Gauss elimination depends on that condition of the matrix. And then we'll jump back into like tying it back into module 2 with data processing. We can do linear regression, but now it's for any function. Like it doesn't just have to be straight lines or polynomial fits. Cool. Yeah.
Can you go through again? I think briefly talked about it last class, but the conditioning of a matrix in that first module.
Yeah.
I don't quite understand it.
It's kind of a weird thing to think about, like the condition of the matrix. So let's skip down to where we're talking about the condition. So there's that. So here, sometimes it helps to think about it. It's like a so like if we're just trying to solve one problem, one linear problem, and our coefficient is 3, the output is 6, then I could think of this like as a 1-by-1 matrix. So A equals 1, X is just like some unknown X1 vector, and B is 6. Kind of a boring linear algebra problem to solve, and you probably solved it in your head already. And for every 1-by-1 matrix, like so A is 1, Or sorry, not 3. A is 3. Oh my god. Halloween. So A inverse. This one's kind of, it's easy to calculate like a 1 by 1 inverse because it's just 1 over that. So when I'm thinking about like the condition of this matrix, no matter what value I use for like magnitude, however I want to describe the magnitude of that matrix, the norm of it, for 1 by 1, it's always going to be 1. So there's never, when you're solving one linear equation, a computer is never going to like introduce, it's always well conditioned. Like it's always a very easy problem to solve.
So conditioning is akin to how easily it's solved.
Yeah. So really high condition numbers mean that A and A inverse are like there's something really big happening.
Is 1 the highest value or no?
No, 1, usually 1 or smaller. I think that would be the smallest value for the condition number. I'm pretty sure 1 would be like the lowest condition number because you're always taking like 2 magnitudes and multiplying them together. So I think and if if we thought of like the magnitude of A of like it was 1/3, then the inverse is probably going to be 3 or bigger. So then you'd end up at 1. But that's like the 1 by 1 example. And versus actually like in the 2 by 2 example, if I'm trying to take inverse of something that's not really invertible, here we can do it 1 1 2 2. And then what is the inverse? I think it's 1 over determinant times.
You swap
I think you swap this B and
last, and then you change the sign of the two.
I think that's our main like coefficients, right? -1, -2, like switch the sign.
The other way.
Is it?
Yeah, the other way.
Sorry. All right, so 2 1 -1 -2. Let's try that. And then multiplied by 1 over 2 times 1 minus 2 times 1. So this, like all the coefficients are infinite in this case. Here we can add something small to both of them. Which ones did I do? Just that top one. So I could add like plus D up there. So now this one's going to be 1 plus D, and then it'll be 2 . 2 plus 2d minus 2. So all this is 2, negative 1, negative 2, 1 plus d times 1 over 2d. So the smaller d gets, the closer all the numbers inside my matrix are going to be, at least the inverse, are going to be infinite. So no matter how I choose the magnitude, whatever norm I want to do, like max of each row or max of each column, they're all going to be really big numbers if d is small.
That means you take the condition where you multiply A by A inverse.
Yeah.
You're going to get basically an infinite number as long as D
Yeah.
is. And so what does that represent then?
So if your condition number is infinite, like in this case it is infinity, because I can take the inverse and show like, okay, here's the inverse, but it's definitely infinite. So if it's infinite, then you can't really solve that problem, because there are infinite solutions to that set of equations.
So you don't want a large condition.
Yeah, ideally you want condition numbers that are small.
Okay.
Yeah. And roughly the number that we're trying to hit, because we deal with 64-bit floating point numbers all the time, 10 to the negative 16 is that, or sorry, that's our error. But 10 to the whenever we think about like the error is 10 to the c minus, I think I call it t in here, right? Like the accuracy of any number that we're calculating, at least if we're going to do math, if we're going to multiply, add, subtract, best we can do with 64-bit numbers is 10 to the negative 16. Anything smaller than that is 0, because we can't add it to something else. So our accuracy is 10 to the negative 16. So if our when we try to do linear algebra, and we're saying, hey, computer, solve this set of equations, if that condition number is bigger than 10 to the 16, then we're starting to introduce like order, like 10 to the 1, or 10 to the 0, so like 1, plus or minus 1. If it's bigger than that, like 10 to the 20, then now we're starting to introduce like 1,000, that whatever value we get could be plus or minus 1,000 on our solutions.
So when it spits out the condition value using the Linnell condition,
yeah,
and that number comes out to something to 10 to the 15.
Yeah.
What is that saying? That's saying it's a really high conditioning value.
That means that it's very high, and so the error
is very large.
The error at 10 to the 15. So if we say condition of A is 10 to the 15, error is going to be 10 to the 15 minus 16, or 10 to the negative 1. So
you're 10 to the 10th decimal place.
Yeah, like 0.1.
Your solution is, the error of your solution is within the 0.1 magnitude.
Yeah. So if you're trying to report like 1/10 of a millimeter, and all your solutions are 0.1, 0.3, like really it's plus or minus 0.1 for all of those.
So can your condition get to a value greater than 10 to the 16?
Yeah, we can
So
have.
It could be something like 10 to the 18, and all of a sudden your error is, 10 squared.
Yeah, like here. Yeah, like in this case we had 10 to the 15. Let's say 1e negative 16. Yeah, when I try to add something smaller than, if d is less than that floating point, the epsilon, then it doesn't actually add to that first term, so I get a singular matrix error, and the condition number is 10 to the 16 in this case. I think it could be bigger than 10 to the 16, like if you get bigger matrices. Like,
So then saying your solution, whatever that solution is a plus or minus error range, basically 1.
Yeah,
okay.
yeah. Yeah, like as we, as this d number keeps decreasing, it's kind of weird. Yeah, if we're kind of working our way backwards, like it starts off at 0.6 and 3.6 and then goes into 1 and 4, negative 1 and 4. So the answer is changing. I mean, it should change a little bit, but d is really small, so it should be basically the same number.
When you're setting up that array for y, fill condition, why is it 3 comma 6 plus b? Where does I'm confused how you're getting that side. If you just scroll up slightly to see what the equations were with delta in there.
Oh, yeah. I guess I put it down here, huh? Really, I put it in here. I don't know why I put it over there. Because that's what I have written up there. And there we start to see like even bigger differences. Yeah, because changing from like 10 to the negative 15 to 5 to the negative 15, we shouldn't, if it was a regular like well-conditioned matrix, then these should be the same numbers. Like we only change things by 5 times 10 to the negative 16, but they're getting bigger. The changes keep making bigger changes there.
Because if you didn't have the delta involved in there, it would just be a singular matrix, right?
That one would be singular, and it just gives us an error saying like, hey, you can't solve this.
It's the same equation.
Yeah, yeah. Yeah. Cool. Yeah, if you're wondering like how all this connects into homework, in this first problem, we should see that this solution is singular in case 1 versus case 2 is very easy to solve. linear algebra problem. And then other part is, where is it? Oh no. Did I get rid of it? Maybe. Does it ask you to? Yeah, the Hilbert matrix. I don't know why mine doesn't have that. Did I delete it? Oh no, here it is. Okay, so Hilbert matrix. This is, it's an example of a matrix that is not singular, but the bigger it gets, the closer, the more ill-conditioned it becomes. And you can write out a function to like create the Hilbert matrix. I think NumPy has a Hilbert matrix in there. If you want the, that's the real like Python way of doing something. It's like from Python import the thing I want to do, run it. Is it SciPy? I thought it was. Oh, maybe it's scipy.linalg. So if you want, you can program it yourself, or you can say and a 1-by-1 Hilbert matrix is just going to be a 1 versus the 5-by-5. It starts off at 1, but along the diagonal kind of goes 1, 1/3, 1/5, 1/7, 1/9. It just keeps the diagonal values keep getting smaller, and kind of this cross diagonal here, 1/2, 1/3, 1/4. And this is the formula for it, of like how to get to that same output. The only tricky part is that this is using I and J base 1, so it's 1. So in the very first one, it's 1 + 1 - 1. For Python, it's going to be 0 + 0 + 1. So you add 1 instead of subtracting. But if I look at the condition number here, that it starts off in the like 500,000, so not unsolvable, but not 1. It's not our like single linear equation that we're trying to solve. Versus like a 50-by-50 Hilbert matrix, now we're talking like 10 to the 19. So as we try to solve this, the error that we would introduce would be 10 to the 19 minus 15, so like 10 to the 4 sort of error. And at one point, somebody did this one time. I thought it was kind of cool. Like calculate all the, I guess we should start at 1, huh? And I should probably import stuff that I want. If we go from like 1 to 49 of like matrix keeps getting bigger, and compare like what is the condition number as it keeps getting bigger, doesn't make a lot of sense there. So we'll do a semi-log y and start to see like it shoots up to like 10 to the 17, then at some point it just sort of fizzles out. Like it's kind of increasing after there, but for the most part what we're seeing is that it's getting harder and harder to actually calculate the condition number. Like we don't even have the floating point spaces to save the inverse and calculate that norm. So I think even if you go bigger, yeah, it just kind of fizzles out around 10 to the 19. So that might be roughly upper limit to like how badly conditioned something can be. It's probably about 10 to the 19, 10 to the 20. Really, we could probably skip that 1 by 1, right? First it looks kind of, the condition number looks well behaved, but then I think we are just hitting round off error just from the computer at that point. So I'm just taking like the condition number, finding what power is it, like 10 to the 8 versus 10 to the 16, and then subtracting out that like a 10 to the negative 16. So 10 to the condition number minus how well we could store the numbers. It's given kind of transforming that first curve into how much error. So the bigger the condition number, the more error we would get in the solution, just based on how floating point operations tend to, like how they work in the computer as you're like flipping bits back and forth. And the other thing, kind of like the hard part, but like once you have the process down, it's always the same of setting up a linear algebra problem, is like identifying what's known, what's unknown, and how do I get the computer to do the work for me. So in this case, I have 5 equations to relate like all the different deflections of piston 1, piston 2, 3, 4, and 5. So I'm not trying to solve like function of time or anything. I'm just trying to say like, all right, I have these forces, it's squishing things. What are the equations that describe where they are? So so all of the x values, I don't know what they are, but I do know that they're creating a force. The bigger the x, the more force the spring is creating. So I can kind of set up those equations and just pull out, and now I'm trying to pull out all of the known spring constants away from those actual unknown x positions. So like a k1 and a negative k1 for that first equation, and then the x3, 4, and 5 don't show up in equation 1, so a bunch of zeros. And then in equation 2, I have x2, x1, and x3, and there's coefficients for all of those, but x4, x5 don't affect the position of x2, at least not directly. They're all connected because it is a linear algebra, linear set of equations, but and then same thing, kind of running down that list, and then all those f and 0 and 0, 0, and negative f, kind of those applied forces, like the right hand side. And once I have all that stuff, those are like real numbers that I can plug into the computer, and then the x values are going to be the output of when I say, okay, solve this problem for me. What is the answer? So we'll do some fancy how do I use what am I doing wrong? It is 1D. 5 is a one-dimensional number. What am I doing wrong there? Does anybody else? To get a diagonal matrix? No?
It should have the, like, empty dot diagonal, empty dot 1 is 5.
But can I just give it the shape?
I don't know.
I thought I could just say... I thought I could just say, like... Alright, yeah, I can do that. So only missing part there is that 0, 0 should be 1, and -1, -1 is 1. And now F is going to be -1, 0, 0, 0, -1. And then I'm getting this singular matrix because there are, I mean, looking at this figure, kind of thinking about like what could happen. I could apply F. It could be that 3 moves nowhere, that 3 is my axis of symmetry and everything else is squishing towards it. Or it could be that x1 moved, like x1 was held fixed and x5 moved towards it. So there's an infinite number of ways to satisfy these equations, because one of the equations that I'm kind of solving is that that a positive f is equal to negative f. But we already knew that. They're like f minus f equals 0, but we already knew that. So we need some kind of like fixed point, at least if we want to use linear algebra to solve it. Fix over. So we can go colon -1, colon -1, and colon -1, just ignoring the last row, last column of k, and the last value of f. And then we get 4, 3, 2, 1. The x1 moved 4 units, x3 moved 3, x2 moved 2, and then x4 moved 1 unit towards x5. So my input was those first 4 rows, 4 columns of k, and then just those first 4 inputs of f. So that I could actually get an output of like 4, 3, 2, 1. works, and it's pretty fast. Easier than doing it out by hand, solving 5 equations, 5 unknowns. Here are 4 equations, 4 unknowns. Yeah. If since I got an answer, this is the second case because it actually gave me an answer. I guess what I could do is paste another copy of it and show just the first case. So in the first case, what I'm trying to say, like, all right, here's my big K matrix with no boundary conditions, singular. There's it's a long error, but at the base level, it's a singular matrix. Like, there's just no way around it. You're gonna get an error, yeah. Yep. Yeah, I know I've seen, like, people have plugged in different values, like for K1, 2, 3, and 4, and somehow gotten it to work out. And I can reproduce it. Like, sometimes you can get an answer, like it just happens. But the answer is like, it doesn't make sense. Like, it doesn't even make physical sense. It does solve the equations though. Like, it does satisfy. It is one solution for this like set of forces and springs. But it doesn't make sense that there's only one solution for case 1. Cool. All right. Have a great weekend.